All right, we have here another example of a collision. We have a father who is ice skating west. So I'm going to label this as dad instead of an F so we don't confuse that with final. Dad has a mass of 70 kilograms. I'm going to label this as V sub D for dad. He is ice skating west, collides with his 30 kilogram son. So son is ice skating north. The son has a mass of 30 kilograms. So immediately after the collision, the father and son are observed to be moving together. So dad is a nice father, and he grabs his son so he doesn't knock him over. And we find that they are traveling together at 2 meters per second in a direction of 37 degrees north of west immediately after the collision. So we're not thinking about the time to slow down, stop. When we're talking about these collisions and we're talking about the impulse, we're talking about the very short time frame of the collision itself. Now, because the motion of both dad and son change because of their interaction, we can use conservation of momentum. So when we use conservation of momentum, we need to define our system. So our system needs to involve everyone that is in the collision, so all two of them, dad and son. If we call dad object 1 and son object 2, we can say that M1 V1 initial plus M2 V2 initial has to equal, well, dad is picking up son. They're moving together. This makes the collision perfectly or totally inelastic. And so we can combine their masses. They will be traveling at with the same final velocity. All right, so momentum is conserved. P initial of the system is equal to P final of the system. All right, now momentum is a vector. So similar to when we were solving problems with forces that were vectors or with motion that were vectors, we had to look at the x components separately from the y components. And that is true here as well. So let's see. So I'm using this equation, conservation of momentum, but let's look at it for x specifically. If dad is object 1, dad is moving in the x direction. Dad has a mass of 70 kilograms, and he's moving to the left with some unknown velocity. This is one of the values we're trying to find, is actually the speed. We already know the direction he's traveling in. The son has a mass of 30, but he has no x component of motion. And so we end up with 0 for the M2 V2 initial portion of our equation. That needs to equal their combined mass times specifically the Vx final, the x component of the velocity. So they've told us, I'm going to just draw this bigger, that together they are traveling at 2 meters per second at this angle of 37 degrees. Vx final is to the left, and if we know the hypotenuse there, the magnitude of the vector is 2 meters per second. When we multiply by cosine of 37, that gives us the x component finally. That's what I need to put right here. Okay, so that coming up to our basic equation, V final, this is specifically the x component. So right now we have negative 70 times the speed of Dad. The negative sign accounted for the direction. Let's see, 30 and 70 is 100, so minus 200 cosine 37. We can solve for the speed of Dad right here. The negative signs will cancel. Let's see, times the cosine of 37 divided by 70. Oops, put that in wrong. I'll try that again. 200 cosine 37 divided by 70. 2.28, so we have 2 sig figs maybe, so 2.3 meters per second is how fast Dad is ice skating at that moment. Meaning the moment right before he collides into his son, right before he picks up his son. That's considered a collision, even if he's picking him up. So we find Dad's speed from momentum conservation in the x direction. We use the same equation again, but accounting for y components of velocity. So Dad has no velocity in the y direction initially. He was moving only in the x direction. The sun is moving north. That's completely the y direction. So I'm going to just call him V sub s for sun. So that has to equal their combined mass times the final y component of the velocity, which we have to come back here to our triangle. Vy final is upwards. It's going to be 2 times the sine of 37. So that's what we want to put in over here, because we're taking the mass times the velocity, and specifically the y component. So 30 v sun is equal to 200 sine 37. Plugging these numbers in will give us how fast the sun was traveling right before the collision. So the sun was traveling 4 meters per second, almost twice the speed of Dad. But again, to get an angle of 37, ultimately we could draw a triangle that represents the momentum of the sun plus the momentum of Dad. Those are adding to the overall total momentum. That total momentum is determined by the momentum of the sun and Dad individually. And you could add those in terms of momentum and not just velocity. We broke down the velocities and then multiplied by the mass, but you could multiply by the mass and then find the x and y components of momentum. Ultimately, it's the same thing. But again, if motion is going to be both in the x and y direction, we need to break down our conservation of momentum in terms of both directions individually.